Hey guys, welcome back. I hope you enjoyed the game we played yesterday, Greedy Pig. If you're in class today, we're going to end up playing a second round. We might even play it again some other time later. The game is really more fun if you have other people to play against, so even though I tried to show you the game yesterday if you're doing distance learning, it's just one of those things that you kind of it's more fun with other people. So we will talk about the probability behind picking the best strategy for a greedy pig today. So spoilers there. All right, but today we're going to move on to our next chapter, chapter 16, and probability models. And we'll start out by looking into the geometric model. Then tomorrow or the next day, I'm not sure which one, but we'll go into binomial distribution, and then after that we'll start using bell curves and pretty much be using bell curves for the rest of the year. So we will be taking the test, I think, in about 2 weeks. So about 2 weeks we'll be taking the test for probability, and that's when your quiz score will be replaced with your test score anyway. So we're going to go back to the example of the cereal boxes with the 3 playing cards. We have the Danica, LeBron James, and the Serena Williams. I actually made these cards, which is pretty stinking cool. Like, I made the templates. I don't know if you can see them. Oh, no. Okay, anyway, I made the templates and then I found the images and put them together. It was quite fun. Anyway, apparently I had a lot of time on my hands last year. So let's say that 30% of cereal boxes have a Danica Patrick in them, 20% have a LeBron James, and then all the rest of them have Serena Williams, which would be 50%. So we want to answer questions about, like, for example, how many boxes would we expect to have to open before we find our first LeBron James card? The last time we simulated and we answered questions like collecting all 3. So we did simulations to look at, okay, so how many boxes would we expect to have to open before we found all 3? And I don't remember what our answer for that one was, but we'll be doing a simulation this time to basically answer the question, how many until our first success? And that is really a geometric model. So suppose the cereal manufacturer puts pictures of famous athletes on the cards of each cereal box. 20% of the cards contain LeBron, 30% Danica Patrick, and the rest Serena Williams. Pretty much what we just talked about. So what's the probability our first LeBron card is in the third box that we open? Well, this is really conditional probability because each event would be like the first box, which either was successful or not, the second box, which either had LeBron in it or not, and the third box that either had it or not. So we could find our first success on the first box, right, which would be 20% of the time, but then 80% of the time we would get something else, either Danica Patrick or Serena Williams. And then we have our second event. Now, if you notice, the probabilities, the conditional probabilities, stay exactly the same. That's because it's independent. So regardless of what happened on the first box, the probabilities of finding them on the second box is still going to be exactly the same. So 20% or 80%. So, and then the third box would be 20% or 80% as well. So what's the probability the first one we find is on the third box? Well, that means the first 2 events that had to have happened is that we didn't have it, and the third one is that we did have it. So it would be 0.8 squared. Oh my gosh, my handwriting. 0.8 squared times 0.2, which is going to give us some value, whatever that is. Anyway, too lazy to put it in the calculator. So what's that probability? I don't know. Put it in the calculator to figure it out. Okay, so answering questions like that is when geometric model comes in, but that trial is actually what we call a Bernoulli trial. So this is Daniel Bernoulli. You might know him and his famous brother. I think it might be Jacob Bernoulli. Daniel and Jacob Bernoulli, the Bernoulli brothers from physics, and so you might talk about Bernoulli principle with fluid dynamics and stuff like that. So anyway, they were mathematicians and physicists. And yeah, anyway, some really cool stories. I don't know all the story behind them, but I know one of my friends in college did a project over them for the history of math, and he said that it was actually pretty cool. So I think they were Swiss mathematicians or Italian. I don't remember. Anyway, so what is a Bernoulli trial? A Bernoulli trial is when you only have 2 possible outcomes, success or failure. The probability of success, we denote it as a P. I don't know why, maybe for probability. And then we use a Q. And the reason it's Q, I guess, is because Q follows P in the alphabet, and we haven't used Q for anything in stats yet. But anyway, failures will be denoted as Qs, And Q, the probability of failure is just going to be 1 minus the probability of success. So if 20% of them were successful, then 80% would be our failure rate of getting something besides what we were looking for, like in LeBron James card. All right, then the third part for Bernoulli trials, that it must be independent. So each event that we do, whatever happened in the past, must be independent of what's going to happen next, so it doesn't actually change the probabilities, like we saw with our tree diagram here. Regardless of what happened, the probability of success remained constant. So that means it must be independent. So it's basically there's two outcomes: success or failure, success or failure, success or failure. They're all independent of each other, and whatever the probability of success is, the probability of failure is 1 minus that. So 1 minus 0.2 would be the 0.8. All right, so those are Bernoulli trials. And when we have Bernoulli trials, we can build upon those with a geometric model, which models how long till the first success, and then a binomial model as well, which is probably more interesting, which will model out of like 5 trials, how many successes would we expect to have, which would be the binomial distribution, which we'll talk about more later. So an example of Bernoulli trials are like not rolling a dice, because they're, unless you were looking for a specific outcome, like rolling a 3 or something like that, because that we'd have to define something as a success and then anything else that we got as a failure. A good for dice, but they are independent, so that part's going to work. For instance, Shaq's free throws, even though his probability of success might be like, I don't know, 46%. I shouldn't throw shade. He's a lot bigger than I am. But anyway, yes, probability of success, probability of failure. Is it independent? That's actually kind of a cool conversation. So if you miss your first free throw, are you more likely to miss the second one? Are you more likely to like slow down and focus and go through your routine and more likely to make it the second time? I don't know. Statisticians have debated that, and I guess we'd have to look at observations to see if we believe, depending on, actually, that's all you'd have to do. Let's look at their first free throw and then their second one, and look at the overall, the marginal for that player, and then see if they're more likely to make their second ones than they are the first one. So that sounds fun. Why don't we do that? But that's probably, I don't know if we've ever collected stats about that before. I should look into it, but it's already 1 o'clock in the morning and I'm still recording and haven't done geometry. So I'm not going to look into it today. Maybe tomorrow, because tomorrow is like my recovery day. Anyway, flipping a coin, success or failure. Define one of them as a success and the other one as a failure. They're independent, good to go. All right, so the geometric model is waiting for the first success. So let's say, what's the probability of first success was on the third one, which means that we'd be using geometric PDF, which is probability density function. Our probability in this case would be 20%. That's a probability of a success. And then the number that we're looking for is the success on the third one, the third event, so that would be a 3. So basically what it would look like is 0.8 squared, and then times 0.2. And the reason it's 0.8 squared, because that's the number of failures we'd have to have before our first success. And if our first success was on the third one, that would mean there were 2 failures before it, which is just this x minus 1, right? Where x was 3, so 3 minus 1 would be 2. So essentially, if our probability of our success on the first one would mean there were 0 failures before, so that would be 0.2. Probability of first success was on the second one would mean there was 1 failure and 1 success. And then the probability of this first success was on the third one means there were 2 failures before our first success, which here. So they just keeps going on. So if you notice, every time we go to the next one, so what's geometric PDF for 4 or for 5, or the first success was on the 5th one or 7th one or 8th one or whatever, we're just multiplying an additional failure that had to happen before it. So our probabilities are always going to keep shrinking. So the biggest one we have is going to be 0.2. That's the most likely on the geometric probability. The most likely will always be the first success would be on the first one, because every additional one for geometric would require a failure to have occurred before, which is interesting, which means that our shape is going to be skewed to the right, and I'll show you that in just a little bit. So what is the expected value of a geometric model, or like the average? So basically, how long would we expect to have to wait before our first success, which is actually kind of a cool question. So like with our game we played with the dice, right? Or we'll do the coin example first. So if the probability of success of, like, say we're going to count ahead as success, on average, how long would we have to wait before we get ahead? So on average, it would be every 2 coin tosses, right? Sometimes it might take 3 or 4 or 5 or more before we get our first head. Sometimes we'll get our first head on the first one, but on average, we would expect to get our first head and 2 coin flips. What about a dice? So let's say that we wanted to roll a 5, or we don't want to roll a 5, right? the probability of success would be 1/6 for whatever outcome we set it to be. And then so we would expect to roll a 5. How often? 1 out of every 6. So on average, every 6 dice we roll would be a 5, right? On average. What about LeBron? Well, that would be 0.2. So how many? Well, if we looked at the pattern here, if we went, let's try to establish that real quick. So if this was 1/2, so if I wrote the probability as 1/2, and then we said that we would expect our first success on every 2, what's going on here? If we said that a probability was 1/6, we would expect our first success on average every 6. So if you see what's happening here is we're basically taking the reciprocal. We're flipping the numerator and denominator. So be a little bit more interesting to explain that in class so I can read your reactions. But here, so what would we do for LeBron? Well, the expected value or the average for a geometric model is going to be 1 divided by whatever the probability is. And if you're doing 1 divided by the probability, that's also to the -1 power, or the reciprocal power. So if we put that in the calculator, we can do 0.2, and the reciprocal button is actually so common that it has its own button like squaring, which means we would expect a LeBron James card on average every 5 boxes that we open. You could also find that by doing, oops, didn't mean to do that, by doing 1 divided by 0.2, which will give you the exact same thing, which is basically 5. Yeah. Okay, cool. All right. So what's the probability that the first LeBron card is in one of our first 3 boxes? Well, it could have been in the first box, it could have been in the second box, it could have been in the third box, and those are the probabilities there. So that would mean there was 1 failure, 1 success, and then 2 failures, 1 success. Anyway, so if we want to know that it's probability that it's in one of the first 3 boxes, there's really 3 distinct outcomes we could have. It could be in the first one, the second one, or the third one. So we need to add up all the probability density functions going all the way up to 3. Well, that's where we get the cumulative density function, which is going to be the first one plus the second one plus the third one. And we want to add all those together, which would mean the geometric CDF of 0.2 and then 0.3. By the way, let me show you where those are found in the calculator. So it's going to be in our distribution menu, so second, variables, arrow to the very bottom, and we have geometric CDF and PDF. So if we want to find the geometric PDF for like one of these, for instance, we'll do this one right here. So the probability of success is 0.2. Say our first success was on the third one, hit paste, and that'll give us our answer of 1.28, which is exactly what we got. So let's do the geometric CDF, which is a cumulative density function, kind of like an integral or an area under the curve, and we're going to go up to 3. So we want to know that it happened within the first 3. So same thing, go to second, variables, arrow to the bottom for the CDF. Our probability is still 0.2 for success, and we want to know within the first 3, then hit paste, and that's it. And it's going to add all those together, and sure enough, that's exactly what we get. Let me go ahead and bring up, if you look on the homework, I gave you a link for the geometric distribution. It's an applet. It's really, really nice. I'm going to go ahead and pull it up. All right, so here's our applet. I'll give you guys the link for it. You can also just Google search geometric distribution applet. And it'll be the first one that comes up. It's from the University of Iowa, apparently from their Department of Stats and Actuarial Science, which we remember actuarial science, like what my brother-in-law does, just has to do with insurance and statistics. So kind of cool. So thank you, University of Iowa. Matt Bognar. Anyway, so basically we want to graph out the geometric distribution, and you can use this applet. I would actually have it up on your iPad while you're doing the work if you can, I don't know, but it's really nice to help visualize what's going on as you do this. So our probability of success was 0.2. All right, and then that's going to graph out the shape. So the probability of first success was on the first one. This is one thing I don't like about it. Their x-axis here is basically shifted off 1. So they're basically counting the number of failures before the first success, but our calculator counts till the first success. So instead of 0, we would really say 1. So take that with a grain of salt, but everything else is just fine with this. So the probability of first success, meaning we had 0 failures, would be 0.2, and then 0.8 times 0.2 would be, for us for 2, would be 0.16, and then 0.128. So this should look familiar. And basically each time we're just adding another failure, so we're multiplying it by 0.8 again and again, and it's just going to keep getting smaller and smaller until you have like diminishing returns, and basically it goes to 0 after a while. Statistically 0. All right, so what's the probability? And remember, you got to adjust this. So the probability we have our first success within the first 3. Now I'm going to do 2 because That means that we had 2 failures before our first success. I don't know, it's kind of weird. So this is going to be a PDF for each individual one of these. But if you want to know the CDF, we can do less than or equal to, and it'll find the first 3 of them here and add them all together, and that'll give us this value. So if you want to visualize what's going on, just keep in mind the x-axis is going to be shifted off 1 less than whatever you put in the calculator, but you can visualize it as you go, and it's actually pretty stinking cool. All right, so good stuff. Hopefully you see the difference between PDF and the CDF there with the area under the curve. All right, so Bernoulli trials. It's on page 414 if you want to read about it. There are 2 possible outcomes, success and failure, P and Q. Probability of success is constant, meaning it's independent events. And, probability of success must remain constant. In other words, the trials have to be independent of each other. It's kind of the same thing. And then, the only other thing is the probability of success is 1 minus the probability of failure. That's the only other thing that didn't list on this one for some reason. All right, several random events that are Bernoulli trials, like flipping a coin, free throws in basketball, selecting a defective product on the assembly line, different stuff like that. So here's our geometric model. The number X is the number of trials until the first success. So we have 1 minus the number of trials, blah, blah, blah. We will have X minus 1 unsuccessful trials before our first successful, which would be the X trial. The expected value, which is when we would expect to have our first success on average, would be 1 over P, or P to the negative 1 power. And that's where it's centered at. So for our example with our 0.2 for LeBron, that would be every 4 boxes. We would expect, if I had that right. Oh no, it would actually be every 5 boxes, but it would be showing up 4 here because it was minus 1. So anyway, and then the standard deviation is going to be the square root of Q divided by P squared. Now, we're actually never going to use the standard deviation of a geometric model. The reason we use mean and standard deviation is so that we can apply a normal model. But on this one, clearly you can see it's skewed to the right, so it's not appropriate to use a normal model. We don't expect 68% of all of our potential outcomes or whatever for the geometric model to be within 1 standard deviation of the mean. In this case, I think the standard deviation was 4, centered at 4, but it's really 5 because remember the whole thing was off 1. Clearly that doesn't fit it very well. And also you see that our standard deviation is going to be, because it's skewed to the right, that skewedness is going to increase our deviations. And so they're not all packed around the center like we would expect. And so we're actually going to have a larger standard deviation than what would actually fit it. So it should be a smaller model because of those outliers in the tail. All right, so anyway, basically all you need to know is 1 over P, or P to the 1 half, negative 1 power. All right, 10% condition. Okay, so when we're sampling without replacement, like for instance, like pulling marbles out of a jar or something like that, if we sample without replacement, we would have like success or failure, but every time we remove a marble and we don't put it back, the probabilities are changing. So technically it's not actually, it's not independent. So we can actually override that with something called the 10% condition. So this happens to do with sampling without condition when we're talking about Bernoulli trials here. All right, so as long as we're sampling less than 10% of the population, it's okay because the probabilities are going to change, but the difference in the probabilities is going to be really small. Now, once we start sampling more than 10% of the population, then we start getting into issues. So if we have a deck of 52 cards, as long as we're sampling less than 5 cards, technically every time the probabilities are going to change, but we're going to say that it's okay and override the assumption of independence with the 10% condition, and we'll be able to move on just fine. Okay. So assumptions versus conditions. The assumption of independence is required, right? But if you can't assume that it's independent because we know we're sampling without replacement and they're not independent, then as long as we're sampling less than 10%, that condition will override the independence assumption and allow us to proceed. All right, so let's talk about greedy pig and look at it through the lens of random variables. So let's calculate the expected value for the outcome on each roll. So P will be our current number of points, whatever you have. Notice that there's a 1/6 chance that P increases by 1, 2, 3, 4, or 6. But whenever we roll a 5, then your number of points is going to go to 0, and that could happen 1 out of 6 times, right? So basically our expected value, these are all the possible outcomes. So the number of points you had from the previous round could either go up by 1 out of 6 at a time, go up by 2, 3, 4, or 6. But whenever we get to the 5, then it goes to 0 and you don't have any points left over. So these are all of our possible outcomes and their weights. They're all weighed the same, so we can divide them all by 6 and add them together. We had basically 5 p's plus a 16 divided by 6, so kind of nice. That would be our expected value, so the number of points you have plus times 5 plus 16 divided by 6. All right, so the next part we're going to do is, it's actually shown up pretty nice, I believe, on your assignment if you want to read it. But I'm going to skip some steps because it gets kind of annoying. Basically, we split both of these by the denominator by 6, and then we subtract 5p divided by 6 to the other side. We factor out the p, and then we do some multiplication. We end up with p is going to be greater than, the number of points is greater than 16 divided by 6 times 6, which reduces to p is greater than 16. So whenever the number of points you have is greater than 16, that's when we kind of optimize the our strategy. So whenever you have more than 16 points, then the expected number of points you would have from the next round by playing again is less than the number of points you have right now, and so you should stop playing. So anytime that you get to up to 16, you should stop. And in the long run, this will be the optimum strategy, the best strategy. So if we play this game again, you can believe this strategy or you can not believe this strategy, and we can see how it works out. But if everyone runs the same strategy, then everyone will win, and I will run out of candy. So keep that in mind. All right, so the PDF. Geometric PDF, you can read that if you're still struggling with it. Basically, it's how long until the first success. The CDF would be a cumulative density function that would add those all together up to a certain amount. So CDF, again, would add them together. You can read that if you need to. Let's look at number 3, simulating the geometric model. So think about LeBron James picture search again. You're opening boxes of serial one at a time looking for his picture, which is in 20% of the boxes. You want to know how many boxes you might have to open in order to find your first LeBron. So we do know what the geometric model is, and we can model that out. But let's try to simulate that model by... I don't know if I told you how many we were doing. Oh no, you'll have to figure out how many. Anyway, so we're going to run as many trials as we can with the integers below, tally the frequencies in row B of the table below. All right, so describe how you're going to simulate it. So we need to assign our outcomes. So we're 20%, so we can use each integer because it ends in 0. So we're going to use 0 and 1 to represent LeBron, and any other integer will represent Danica or Serena. So on the first one, we have 5 in a row, none of them, and then the 6th one would be our first success. So I'm just going to tally that over here. So the frequency, the number of times that it took 6 before we found the first one, is going to go right here. And then 1, 2, 3. So then there were 3 before our first success. So I'm going to put a tally there. And then there's 5, 10, 15, and then don't forget that one, 16, and 17, 18. So this would be our 18th one before our first success, and then 1 before our first success. So I'm going to put a tally for 18, which is just going to go in the 12 or more column. That'd be very rare. In fact, you can see the probability down there. And then 1, which would be right here, which would be our most common one. And then 1, 2, okay, 5, 6, 7, 8, 9, 10, 11, 12. So that would be our 12th. And then 3, and then you'll have to do the rest on your own. So I'm going to put a 1 for the 12, and then 1 more for the 3. Okay, so after you get all of your frequencies done, we're going to find the estimated frequency. So add them all together. I'm not sure how many successes we're going to have. I could pause the video and find it, but just count them, and then find the fraction. So what's our estimated probability from our simulation? So right now we have 1, 2, 3, 4, 5, 6. Yeah, we have 6, so it would be 1 out of 6, 2 out of 6, 1 out of 6, 2 out of 6, right? So obviously we haven't done our simulation long enough in order to do it. But then compare it to the geometric PDF. This is what the probability should be, and we know that from our geometric probability density function model, and see how close it is based on our simulation, which is kind of cool. I enjoy that kind of stuff. All right, so there's the rest of them. You can do that. This is what it should look like, by the way, in case you're curious. So it should be a 20% chance, and then 0.16, 0.28, and it just goes down each time. I kind of showed you that. Then all the ones that were grouped together would be 12%. I don't think I actually had you graph this out. Oh yeah, so then what I want you to do is to actually graph yours out in comparison to this. So this is what it should be with the lines here, and then you can shade it in with whatever your probabilities were for 1 all the way to 12 or more, and see how closely it matches the actual model. This is what it looks like from the applet, by the way, except we started at 1 instead of starting at 0. I know it's kind of weird. I wish they would fix that. Otherwise, if they did, then that applet would be perfect. I'd use it more often in my class. All right, number 10. Suppose a computer chip manufacturer rejects 2% of the chips produced because they fail pre-sale testing. What's the probability that the 5th chip you test is the first bad one you find? So we're counting a success as finding a bad one, which seems odd, but you would think a successful chip would be one that wasn't bad. So yeah, defining your variables is very important. So basically, the probability of finding a bad one is 2%. That's our first, what we're considering a success. So the 5th chip is the first bad one you find. So PDF, geometric PDF, because we're looking for the first success. Probability of success is 0.2. We're looking for 5th one being the first success. It basically means we're going to have 4 failures before a first success. So 0.98, which is a failure to find a defect before 0.2. And when we put that in the calculator, let me see what we get. So second variable, so go to distribution menu, geometric PDF, probability of success 0.12 or 2%. First success was on the 5th one, and then hit paste. Good to go. So that's what we got. What's the probability you find a bad one within the first 10? So it could be any of the first 10. So that's going to be the CDF. Looks like I forgot to change that, which means that answer is probably wrong. Okay, so let's put it in the calculator. So first success, we're doing the CDF. So second variables distribution, CDF, 0.02 is probability of success within the first 10. And there we go. So I think that was, oh, that's interesting because those are very similar fractions, just a decimal off. Okay, so yeah, it was right. I just forgot to update it. So how many do you expect to test before finding a bad one? Well, that's just going to be the reciprocal of it. So all we have to do is do 0.02 to the -1 power, which is that reciprocal button, which is 50. So on average, we'd have to inspect 50 before we find our first bad one. Now, keep in mind how many before a first bad one. We're actually most likely to find it at the first one because its probabilities are going to go down, down, down. But because it's skewed to the right, it's going to move it to 50. So on average, we would expect every 50 to find a bad one. Number 18. An Olympic archer is able to hit a bullseye 80% of the time. Assume each shot is independent of each other, so it would be a Bernoulli trial. If she shoots 6 arrows, find the probability of each of the following results. So her first bullseye comes on the 3rd arrow. So if we're looking for our first success at the geometric probability, model, we're looking at the PDF because we want to know first success was on the 3rd arrow. So it's going to be 0.8 is our success, right? And then times 2. So 0.8 and then 3 would be our first success. So we're going to do second distribution, geometric PDF, 0.8 and 3. And that'll give us a probability of 0.32, which essentially means that we had to have 2 misses before we had our first success or our first bullseye, which would be really rare. We wouldn't expect her to miss twice in a row or miss 2 at all, really. All right, so she misses the bullseye at least once. Anytime we see at least once, our clue is to do the complement. So we're going to find the probability that she doesn't miss at all, which means she hits all of them, which would be 0.8 to the 6th power. And then we put that in the calculator. So we're going to do 1 minus 0.8 caret 6, which is going to give us 7.38%. And I don't think I updated that one. Yeah, I did. Okay, so 7.38%. Her first bullseye comes on the 4th or the 5th arrow. So for this one, we'll do the geometric. Well, we can do it 2 ways. You can either find the probability of the PDF for 4 and then the PDF for 5 and add them together, or you can actually do the CDF for the 5th and then subtract the CDF for the 3rd, and that will give you the difference between those 2 areas would be the 4 and the 5 added together. So I think I'm going to do the CDF. I'm going to do the PDF twice. I think that would be easier. So her first success was on the 4th arrow, which would be this here. And then first success was on the 5th arrow, which would be that right there. Then I'm just going to add those 2 together. So that value plus that value, I think that was pretty easy to follow. So basically it would be 0.768%, and I know I didn't update that. So that's it. All right, so if you have any questions, let me know. We'll be doing two more of these at home before we come back and do another one in person. So do try to make sure you're staying caught up on these. If you guys are getting behind and then we're coming back in class, you're going to be totally lost. So really, you got to make sure that you're staying caught up on the homework. But if you have any questions, let me know, and I'll see you guys later.